Hello again. My name is Scott Arthur. I'm the course leader for D21UD. I hope you enjoyed the class 1 or the introductory lecture. This week we're going to be looking at a little bit more detail in combined and separate systems and also CSOs, and then we'll also think about inputs to the system. Okay, some of what we'll do, particularly in the first half of this class 2A, will be a bit of a recap of some of the issues we covered in the introduction. But I'm a big fan of sort of repeating some of the key themes to try and help people understand what's going on. So hopefully you'll benefit from that. Okay. So we did indeed speak last week about the different kinds of series systems we have. These are combined systems where we have the flows from inside properties, the file flows, and also rainwater combining together into a single pipe, which hopefully goes all the way to the treatment works. We have separate systems where the file flows and the rainwater is kept separately. Now, the third kind of system is a hybrid system, and this is a system which is mostly separate, but the file network has some surface water inflows. Sometimes this is because it's expected that some of the surface water flows will be contaminated, so should go to treatment. Other times it can be because some surface water flows do flush the pipe out to a certain extent. And other times it will just be because of, that was the best solution at the time. So in developed countries, certainly in the EU, we expect around 70% of the network to be combined. And this is really because of the age of quite a lot of developments in developed countries. So that is largely the network that we're currently managing. Because in those systems we have file flow and surface water flows coming together during rainfall events, it means that during rainfall events up to 90% of the flow could be rainwater mixing with the foul sewage, and obviously that's whilst it's deleting the foul sewage, it's also increasing the amount of flow which is going to the treatment works. So it's not economical to size sewer pipes to deal with all the expected rainfall. So typically we expect a pipe to be designed to surcharge once in every 2 years on average. So what does surcharging mean? So if we have a pipe, which is like this, and then we have a manhole shaft that goes up to the surface, what we expect is that most of the time the foul flow, when it's not raining, will be occupying the very bottom of the pipe. During rainfall events, we then expect the flow level to increase. Please excuse my sketch. Once it reaches the top of the pipe diameter, once it goes beyond the top, that's what we call surcharging. Obviously, as a resident living on the surface, I don't really care too much about surcharging in pipe networks. What I'm concerned about is flooding. So that's when the water actually leaves the system itself and starts to cause problems. Okay. Likewise, when that pipe connects down to the wastewater treatment works, normally the treatment works is only designed to cope with 6 times dry weather flow. So flows in excess of that have to be dealt with separately. So we'll come on to how that's dealt with in a couple of slides. Oh, this slide, in fact. So this is how our combined system looks. We have a town which has a pipe network serving it. that pipe network collects both surface water and foul flows, and takes those flows all the way to the treatment works. So during dry weather flow, that's certainly what happens. Now, once we exceed the capacity of the network, so that's once things go beyond surcharging and there starts to run a risk of flooding, the system is then designed to take some of that flow and discharge it via this device called a CSO, a combined sewer overflow, into a neighbouring watercourse. So that could be a river, it might be a lake, or it could be to the sea or an ocean. Obviously that flow is diluted with the rainwater, but it's still 5 to 10% sewage, so it's not the kind of thing you want to go into a river because it has an impact on the environment. So here's a different schematic of how a foul system might look. In the buildings we've got the brown pipes, which are the foul flows. As you can see there, it's collecting water from a wash machine, and I can see someone doing their dishes in the sink, very old fashioned, not using a dishwasher. And we also have the flows from WCs, baths, wash hand basins, etc. And they all come together into the, so they're a foul pipe, and then they connect together into this pipe which is running through the centre of the picture, along with the surface water flows during rainfall events. Now, partway down that we've got the overflow pipe, which is basically our CSO. So once the capacity of our combined pipe is reached, it'll then discharge to the river, which isn't great because you've got the wee boy there feeding the duck, well, looks like cygnets or perhaps goslings in the canal, I think it is. And so that's not great for, it's not a great environment to discharge that to, is it? Because that then has a negative impact on the ecology and biodiversity. So it harms the animals, and it also has a detrimental impact on how people view the space if it becomes quite polluted as well. So this is a more technical look at the how a combined system might look. So you can see that there's really two drivers here. We've got the surfaces on the catchment, and we've got the buildings on the catchment. So the surfaces are what's collecting the rainfall. From listed there, we've got pervious pavement, pervious surfaces, paved surfaces and roofs. They'll discharge to a road drainage system or the roof drainage system, which will then go on to discharge to the combined sewer. Likewise, we've got the building drainage system, and that could be residential, commercial or industrial. That will connect to the building drainage system, and then it will go on to the combined sewer network. Now, some of the rainwater flows will make their way directly, either evaporate, so get too much evaporation in the UK, certainly during rainfall events, or it will make its own way to the watercourse, or it will infiltrate into groundwater. But a lot of it will end up in the combined network, and then it's the job of the sewerage system to take that, hopefully, to the wastewater treatment works. Now, some of it during excess flows might go to CSOs and onto receiving water. So obviously that's not really what we want, but they're there because, remember, the alternative to the CSOs is that we have flooding in the surface, on the surface of the catchment, or we have to spend a lot of extra money making the pipe network even bigger, adding more storage to reduce the CSO spills, which in some instances that is worth doing, but sometimes it can be quite expensive, especially if they're dealing with really rare or unusual events. Sizing the infrastructure to deal with those events can be quite costly, and you end up with infrastructure which is seldom used and expensive to maintain. So combined sewer overflows. So the solution to the capacity issues, as I've just outlined, is CSOs. So during rainfall events, the wastewater and the surface water mix. Flows above a certain setting level, they will be discharged to the environment, and that's called a spill. Flows below that setting level will be passed with treatment. They're called continuation flows. And normally now we'd expect CSOs to be fitted with devices which have the aim of preventing the gross solids, so that's the larger particles, normally classed as being above 6 millimetres. Size of a piece of sweet corn, really, preventing them from leaving the system. So so here we have on the right a sort of picture of what could be a CSO. So we've got on the left of the picture we've got our pipe where the flow is coming towards us, perhaps. During dry weather flow and during small rainfall events, all that flow goes on to the treatment works. During more substantial events, we would expect the flow in that channel to rise, and then where it gets higher than the weir wall, it goes over to the right, and then it goes off to be discharged to the watercourse. Okay. The apparatus on the roof is our depth sensors, so that the people operating the system have some idea of when spills are happening. Not all CSOs have them. So here's a little cartoon picture of how the CSO works. Same as just exactly the same as the previous slide. During dry weather flow, the flow comes in and goes up to treatment. During rainfall events, flow is still coming in and going to treatment, but flow which is over that setting level, it goes off into the watercourse, and who knows what those fish will taste like. Similar diagram, just decluttered. I'll let you look at that at your leisure. So CSOs are actually quite commonplace in most urban areas, so they do exist. What's uncertain when you do see them is how often they're used, and thankfully quite a lot of them have been made redundant, so although they're still visibly there in terms of an outlet on the river, they're perhaps not used at all anymore. So this one's actually the one that's on the cover of the course textbook. There you go. This one's in London, and you can see here, I said earlier that normally the CSOs is fitted with a device to remove the larger particles. This CSO has obviously not got that, so you can see the kind of material that's been discharged into the river. It's less than ideal. But remember, even if those larger solid particles are removed, all that's really doing is stopping the aesthetic pollution from entering the river. There's still lots of other pollution in that flow, which can cause problems. This one's in Edinburgh on the Water of Leith in Stockbridge. So I won't spend a lot of time on this because I went through this in the introductory slides, but basically back in 2004 there's a lot of CSO spills into the River Thames. This resulted in fish kills because the pollutants in the CSO spills consumed the oxygen in the water, and it became quite newsworthy. I then reflected on how this had happened previously in the Victorian era, and an engineer called Joseph Bazalgette came along, and he had intercepted at that time it wasn't CSO spills, it was just the drainage system, the foul drainage system was discharging directly into the River Thames. He intercepted these pipes and he conveyed them downstream. And I made the point that the solution to the problem that was noted in the 2004 news report, which I shared 2 slides ago, the solution to that problem is very similar, in that a large pipe is being created to convey those flows downstream where they can be treated, and so there's less of it going to the River Thames. But that comes at massive cost to protect the environment. So it's worth thinking a little bit about how the CSOs can be configured. So remember, it's the job of the CSO to be like the safety valve in the system. So for most flows, all the flow will go to treatment, even some minor rainfall events, and it's only the bigger rainfall events where it has to direct some of the flow to a water course. So normally this is done by having some sort of weir level, which once the flow reaches a certain height, the flow over that height then gets discharged. And so a simple design is what you see here. This is called the high-sided weir. The design, and this basic design also has some element of solid removal, but this is not good enough to meet environmental standards in the vast majority of cases, certainly these days. So both these pictures show the same CSO, and it's a little bit tricky to understand, so I'll take my time. So the flow, if we look at the picture in the bottom left first, the flow is going from left to right. So during dry weather flow, it's just going right through there. Okay, and on the picture above, that's represented by the circular pipe. Oh, I'm not very good at drawing a circle on this. So the flow just goes straight through. Now in the midsection, the pipe isn't wholly formed. The pipe will just be the lower section, as you can see. If you look at the top right, between those 2 points there, you've really just got the invert of the pipe, and the rest of it then goes into the square channel, which you can see. Square channel with a sloped bottom. The slope's important because once the flow goes back to more dry weather flow conditions again, any solid particles which have deposited on those slope sides are then hopefully washed back into the channel and go to treatment. So what happens during rainfall events is that the flow comes in through the circular pipe, top right again, it begins to rise. So it starts to rise up. Now, so you obviously reach the point where the flow is going to go over and off and away to the river. A very good arrow. And the same on this side, basically. Okay, so that's all fine. Now, so already I can hear you asking, what are these two things here for? Now, so this is about what's so-called good engineering design. So it was about simple steps to stop solid particles from leaving the sewage system and going into the river. And this is one of the approaches that is used. So as the flow comes into that channel, any floating material in the flow will tend to rise up. Let's draw another arrow up. And if the flow is high enough, so just say the flow is up at this level here, the solid particles are maintained between those two baffles. So any solid particles which are in the flow come up, rise up there, and then they're less likely to be washed over the weir and into the river. Okay, so it's quite a simple mechanism that reduced some of the solids flows leaving the system. They were designed so that if the flow got even higher, it would be up and off that way. Yeah, and in that case, that's when you've got a really unusual flow. So then you're making a decision, right? In order to get the discharge capacity you need, you have to neglect the solid retention part of the design, which is not ideal. This is a similar kind of design, quite often seen in tanks. So here you've got, again, we've got the pipe, we've got flow going from left to right. Downstream pipe is smaller, so that's basically the setting level that takes the flow to treatment. Any flow, when the flow is so much that it can't get through that small pipe and then gets spilled to the environment. So same kind of thing, the water level rises, water comes in, solid particles in the flow will rise to the top and they'll just float around on that surface, whilst in this area here to the left, flow comes in and goes off, and off it goes to the watercourse. So again, by means of this, the simple scumboard there, the baffle, that prevents some of the solid particles at least from making it to the environment. So you've still got the design, however, where if the flow coming in is really high, the level gets so high, it could still go over and out. Okay. Right, so this diagram is actually quite good because it also encapsulates how you can reduce your spill frequency. Because basically, if I change my pen colour, basically upstream of the CSO device, you've got this volume here. Okay, so if that was made bigger, so just say it was way up here, that means there's a bigger volume for the flow to fill before we get flow going over the weir. And that's basically how CSO spills have been reduced both in frequency and in volume, is by adding storage either at or the near the CSO to prevent the spill from happening. So since I graduated from university, there's been a big focus in the UK on removing what's called unsatisfactory CSOs, and this list here goes through some of the conditions which might lead to a CSO as being classified as unsatisfactory. So then there's some investment takes place to remove it or reduce the spill frequency or the spill volumes. So some of these are absolutely fundamental. So the first one there is that an unsatisfactory CSO will operate in dry weather conditions. So that means even when it's not raining, it's discharged into the environment, and that is not a good thing. That's absolutely not a good thing at all. It might breach its permit conditions. So you've got a CSO which has a permit, so they've agreed that it will spill so many times per year, and that'll be a limit to a certain volume. If it breaches them, it's unsatisfactory. Will cause significant visual or aesthetic impact due to solids or sewer fungus. Nobody wants sewer fungus in their river, I'm assuming. Cause or significant contribute to deterioration in biological or chemical status of the receiving water, so that's about harming the environment. Cause or significantly contribute to failures in bathing water quality standards for identified bathing waters. So that in the UK, that's largely coastal areas. So you've got a CSO which is discharging into a river, which is then discharging to the sea, and you've then got when the seawater quality is checked for bathing water standards, there's perhaps too high a bacterial count in the water. That means that people bathing in that water end up with ear infections, eye infections, and worse. Shellfish quality, again, water quality standards, and cause pollution to groundwater. So all these things are logical things, and it's these things that triggers some of the investment we've seen in CSO removal or mitigation. So we now expect CSOs to be fitted with perforated screens. So not just the bars we see in the pictures, but normally it's recognised that perforated screens are the best way of retaining solids greater than 6 millimetres. So there's really two types of screens. We've got static screens which rely on the flow directly or indirectly to keep the screen clear. And we've got powered screens which use mechanical processes to keep the screen clear. So in the picture here in the bottom right, you could see we've got the weir wall along there, flow going up and over that is going off to the river, but to get to the river it has to go through that mesh, and that mesh forms a function of the screen, and that will stop those larger particles getting through. Not quite sure how it works, but it looks like there's some sort of device here which will keep that screen clear. So these two graphs here were part of the justification for, certainly in the UK, moving towards screens being on CSOs. And what this compares is so-called good engineering design. So that's just about trying your best to design the CSO to stop solids from moving. And so that's on the left. And on the right, they've got basically, let's just use screens, and that'll stop the solid particles from moving. So what you see is, if you look at, basically what you're doing is you're comparing the y-axis on both these graphs, and you can see that what screens do is for the same situation. So you compare the two yellow dots and two red dots, you've got massive improvements in efficiency. So if you like, if we look at a CSO running at 50% of the peak inflow capacity, so that's right here, it'll be around just over 50% efficient for good engineering design. But with the screen fitted, it's almost 80% efficient, or between 70 and 80% efficient. So that's quite a jump in standard, which is quite good. So there's 101 and probably more different ways that these screens operate. So this one here is one of the ones which doesn't really require power. So there's two real pictures of it here. So basically, as you can see, you look at the left here, the flow comes in through here and goes off to the treatment works. As the flow builds up, and I've got a crazy animation here, as the flow builds up, it fills up that channel there, and eventually a point's reached where it overflows onto the perforated screen. Now obviously what the perforated screen does is it retains those solids bigger than 6 millimeters, and then hopefully it's only the flow that goes through the perforations along with small particles. So next bit. So you can see the flow's coming through. Like I've done it in blue, so it infers that some of the pollution has been removed. Then that section fills up. Now as that section fills up, it floats the solid particles which have been caught on the perforated screen. Okay, and eventually it reaches a point where this part here, the siphon, is activated, because once it gets over there, it's a siphon's formed, and what happens there. So there's the flotation of the solid particles. That's what the brown arrow is for. We've then got the siphon filling, and then once that siphon fills, that draws down the flow in this container quite quickly. Okay, and then the process starts again. But here, when the flow comes over, when the foul flow comes over, the idea is that the solid particles that were caught on the screen, then raised up, they're washed off. The idea is also they're also washed off as the flow drops down as well when the siphon activates. So through those steps, the idea is to keep the screen clear as much as possible. And one can debate about how effective that is over time, and the sort of maintenance cycles required to make sure the screen is completely clear. But that's one of the steps. And so then the waste particles here, the screening's bigger than 6 millimeters are then caught in this channel, and they're washed onto treatment. Okay. So this is another common device which is used, and how this device works is that it encourages a vortex to form inside it, just like you do when you pull the plug out your bath or out your wash hand basin and you see the vortex form. This device is specifically designed for to form a vortex within it. So the inflow comes in here and then goes off to treatment there during dry weather flow. During wet weather, obviously things are running higher. we've got the inflow, outflow still, but then the CSO goes off here. Now, what this spinning is supposed to do is the particles within the flow, it uses centrifugal force to separate them out, and the idea is that these particles within the system end up going out over the overflow and also out to the treatment works, hopefully not over the overflow, and the water that goes over the CSO is a bit cleaner. So that's a little bit about how CSOs work. Of course, the important thing is to think about how we set the setting level, because obviously the higher you set the setting level, the more the watercourse is protected because you've got less fuel spills. So, as I was saying earlier, this has changed over time. So changed over time without doubt. So, and this slide here talks through some of those changes. So, pre-1970, the limit was set at 6 dry weather flow. So anything above, so dry weather flow is the average flow we expect in the network over a week where there's been no rainfall. So it includes weekends, because flow tends to be a little bit different at the weekends. So over that week, it's the average where there's been no rainfall, and that's the dry weather flow. So the CSO is set at 6 times that. Okay, that was back pre-1970. But it was recognised that what that was, well, where do we start with the problems with that? But one of the issues is it was recognised that more affluent areas tend, and it's still the case, tend to use more water. So that means that as well as using more water, their watercourses also had more protection from spills, because they were using more water, and that was used as the multiplier, which didn't really seem like a proper basis. And so this was changed post-1970 to take account of local population numbers and also industrial inputs as well, more directly. Then in 1977, the SED method came along, and this took account of dilution in watercourses. So what this was about was it recognised that there was too much focus on what was happening in the network and the catchment, and using that to decide what was going to go in the watercourse. Whereas if you had a CSO which was discharging into a watercourse which was huge, and you know it was so big compared to the CSO, the volume of CSO spill, it was difficult to quantify even the impact of that. That's completely different from a CSO which was discharging into quite a small stream. So this was recognised in the SDD method, and so a contingency was given for where the dilution was less than 7:1, the setting level would have to be increased. Qualstock came along in the 1980s, and what it did was it also looked at the quality of the watercourse. So if you were discharging to a river which was already highly polluted because of industrial discharges and all sorts of other things, then perhaps the SDD method was adequate. But if it was a really sensitive watercourse with lots of ecology and biodiversity in it, then you had to really think quite carefully. So that was about also managing the risk. And then that process was greater formalised in the 1990s in the UK by the Urban Pollution Method Manual, and it really focused quite a lot of detail in thinking about the receiving water quality when setting levels were set. So this table sums up that kind of approach. So what you see here is in this table, it's saying that if you've got a high amenity watercourse, so that's a watercourse where there's quite a lot of amenity value, if spill frequencies are more than once per year, you want 6mm solid separations. You want 6mm size on your screen. If spill frequencies are less than once a year, then 10 millimetres might be adequate. And that goes down to low amenity or no amenity watercourses, where removing solids using so-called best engineering design, so that's the baffle plates we spoke about a few slides ago, is adequate. So that's what it says on this chart here, but the vast majority of CSOs now do have screens on them of some sort. So design consideration for CSOs, they've got to provide a hydraulic relief, so it's about reducing flood risk. There's got to be some control over how they're running. You've got to minimise operational requirements, so there's no point in having a really fine screen, which is an absolute disaster because it keeps on blocking and causing lots of problems during rainfall events. So you've got to think about that. You've got to think about the risk of the people having to keep it clean during rainfall events if that's an issue, even though you'd be crazy to go in a sewer system during a rainfall event. And that's also about minimising the whole life costs. Okay, so these 6 points here are really just about getting the balance right between preventing flooding, protecting the environment, and making sure it's easy to maintain and not too costly. So lots of problems with CSOs, and I think I've already hinted at what the solution is to CSOs. So in terms of adding storage to the network. So but that's for the existing systems. But when we think of new developments, the decision we make some time ago, well, actually, perhaps the solution to the CSO is simply to remove them from the network entirely and for new networks. And that's where separate systems came along. So we no longer, with a separate system, we no longer mix the combined and foul flows together. We keep them completely separate. So most developments since 1945 in the UK will be separate. To cut costs, the wastewater and surface water pipes are often laid side by side in the same trench. Foul systems are designed to convey your peak wastewater loads. Surface water systems are designed to accommodate given design storms. And normally the aim was to discharge your surface water to the nearest watercourse as quickly as possible. So here's a similar diagram to the one we had earlier, where in our urban development we've got two parallel pipe networks serving the households. One's collecting the foul flows, the other is collecting surface water flows. Foul flows go off to wastewater treatment plant. Surface water flows go to the local watercourse. So under this approach, you've probably got more water going into nearby watercourses before it goes to the treatment work. Well, you've got more surface water. You've got more flows going into nearby watercourses, more than you would have had going over the CSO weir into the watercourse. So obviously that's not so good, but the good thing is in theory you should have no foul sewage going into your watercourse, so that protects the environment from that contamination. And here's this is the surface water element of the surface water system. So you've got the pipe network collecting flows from roofs, etc., into that pipe network, and that pipe network then takes it to nearby watercourses for disposal. But if you look at the river, the fish still don't seem that happy with this. So they've not got a CSO discharging, a few times a year now. What they've got is for every single rainfall event, they've got the surface water getting washed off the catchment surface and into the river. So that's not a good thing, because the surface water does have pollutants in it, which can cause quite a lot of damage to the natural environment. And we'll speak about that in a couple of slides. So here's your surface water drain outlet. This one's on the Braid Burn in Firhill, Oxgangs in Edinburgh. This one's in the Water Leaf, just behind the Sainsbury's in near Longston in Edinburgh. So here we have here's a similar diagram of the combined. Now we've got a surface water system which is it's isolated from the file network. It's taking the flows, doing exactly the same as before. It's taken from the surfaces, taking a pipe network, then taken to the river. But there's no mixing with the file flow at all. There is a risk of cross connections, and that's people either deliberately connecting foul flows to your surface water network because it's cheaper or easier to do, it's legal, or mistakenly doing it. Okay, and you only need a small amount of connections, the misconnections like that to actually cause you quite a lot of trouble. So now all the wastewater is collected in your foul network and it goes to treatment, and it's only after it's treated in your wastewater treatment works does the flow go to the water. So now there's no CSO and there's no untreated sewage going to the watercourse unless you've got a cross connection. So they're not perfect. They're more expensive because you've got much more pipe work. Surface water still carries a pollutant load, and I think there's been more realisation of that over the last 10 or 20 years. Surface water still enters foul sewers via infiltration or inflow. So inflow is water going into your network, which is through a proper connection, but you don't know about it. So it's basically flow you're not expecting, and it causes you trouble. And if only 1% of the connections are incorrect to your surface water, so that's 1% foul flow coming in, you lose a lot of the benefits because the flow is so contaminated. It's a shame. So 3 examples here of how your surface water flows can be contaminated. On the right, we've got where, near where I live in Buxton in Edinburgh, the gas board dug a big hole in the road. They put all the stuff that was in that hole on the road surface. They fixed the gas pipe, and then they put all that, they filled the hole back in again. And what's left behind is this kind of slurry you see on the road surface. Next time it rains, that'll get washed off the road surface and it will go into the surface water pipe where it may clog. If it doesn't clog, it will then get washed onto then it will then get discharged to the river, where it might cause, might be deposited on some wee animals' environment and cause lots of problems there as well. Top left, we've got quite a common scene in the UK. We get pictures like this in local newspapers right across the UK. Councils issue pictures of council workers shoveling grit, and that's because in climates like the UK, we need to put grit on the roads over the winter period to stop them from icing up. In a city like Edinburgh and similar cities, there's thousands of tonnes put on the road every winter. This goes on the road surface, it rains, it gets washed off into the network and gets discharged to the river. Okay, so that's thousands of tonnes of salt going into freshwater streams in Edinburgh. And then we've got on bottom right, we've got the pollution caused by motor vehicles. So here's an oil spill. In addition to leaking oil, you also have partially burnt fuels, which are a big issue. So that's your engine's not burning the fuel properly, particularly when it's not its operating temperature, and sooty deposits come out, and they cause quite a lot of problems. You also have wear of your tyres, general degradation of the vehicles, and wear of the brake discs. The brake discs in particular cause a lot of problems. So the tyre and brake disc problem, tyre wear and brake discs and the partially burnt fuels, they're probably the biggest issue in most urban areas. Where they're most significant is where you have vehicles stopping, accelerating and turning, and where you get that most is big roundabouts and traffic light control junctions. So they tend to be the most polluted parts of the city in terms of surface water runoff. And again, so all 3 of these things and more with separate systems, make their way to urban watercourses and have an impact. So this list here goes through some of the advantages and disadvantages of surface water systems. I'll let you go through this at your leisure. I think I've covered all or most of them already in these slides. So this is the final slide, and I think this is almost interesting. So when I was a student, and that was a long time ago, to be honest, there was a lot of talk back then about what the future of urban drainage was, and back then it was about taking combined networks and decombining them. So getting those combined pipes, removing the surface water inputs to them, and creating a separate, basically a new surface water pipe network that would convey those flows to watercourses. But I think now it's recognised that although that's still the solution in some places, it's recognised that often that's not a solution, because you just end up with all those pollution flow problems in river. So rather than sort of decombining pipe networks as being the future, really what the future is in terms of dealing with, I'm talking about existing developments here, is about retrofitting either storage to combined networks to reduce the spill volumes and also flooding, but also disconnecting the surfaces entirely from the pipe network. So it's not about disconnecting, say, a large car park from a combined network to stop that surface water from going into the combined network and creating a new surface water pipe to take that to a watercourse. It's about disconnecting that large car park and then perhaps directing that flow to a pond or a basin where it's controlled quite locally. So it's no longer about transporting flows away and getting them in watercourses as quickly as possible. It's about how we disconnect those surfaces. In a lot of ways, and dealing with the problem locally, in a lot of ways, is a much more sustainable solution, because you're not taking that big step of decombining networks, creating new pipe networks, discharging to rivers. It's just about disconnecting surfaces and then thinking about how you can be innovative about how you manage that water locally. Okay, so I think the future's changed, is what I'm trying to say. Okay, that's the end of lecture 2A. I hope you found it interesting, and I hope you've learned something along the way, and hopefully there wasn't too much repetition from last week, but I think we did go over some key themes, which I think is good. If you've got any questions, please post them on the discussion board on Vision, or get in touch with me directly. And watch out for lecture 2B. Okay, bye for now.